transistor is a transfer resistor that is used to transmit the current from lower resistance circuit to higher resistance circuit. Used to transmit the current from lower resistance circuit to higher resistance circuit. This transistor consists of two PN junctions joined back to back. Two PN junctions joined back to back. These transistors are of two types, as a PNP transistor and NPN transistor. Before discussing about these two types of transistors, first we should discuss about a transistor. As you can see here, a transistor is a device which mainly consists of three elements. One is emitter, another is base, the last is collector. First, emitter. One end of the transistor, which is a heavily doped region that gives the charge carriers either electrons or holes, is called emitter. This is a heavily doped region consisting of maximum number of impurities like electrons or holes that gives the charge carriers to the base. Next is base. The middle part of the transistor, which is very thin and very lightly doped region, is called base. This base collects all the charge carriers from the emitter and it transfers them to the collector. This collector, this is the other end of the transistor, which is the third region. Physically, this is the biggest region of the transistor, which is moderately doped region. Moderately doped region that collects all the charge carriers from the base. So again I am repeating. One end of the transistor, which is a heavily doped region, is called emitter, which consists of a large number of holes or electrons, which gives the charge carriers to the base. Base is the middle region of the transistor, which is very thin and lightly doped region that collects all the charge carriers from the emitter. And finally, collector. Physically, this is the biggest region of the transistor, which is moderately doped region that collects all the charge carriers from the base. This is the junction between emitter and base. The junction that is present between emitter and base is called emitter junction. This junction present between base and collector is called collector junction. Emitter junction and collector junction. These transistors are classified into two types, as PNP and NPN transistor. Now we shall discuss about the working of PNP and NPN transistors separately. In case of p-side semiconductor, holes are majority charge carriers and electrons are minority charge carriers. This is N side. Electrons are majority charge carriers and holes are minority charge carriers. This p side, again holes are majority charge carriers and electrons are minority charge carriers. This is a hole, this is electron. So in case of PNP transistor, the emitter is made up of P type, base is N type, the collector is of P type. In this transistor, emitter junction is forward bias by connecting P side of the semiconductor to the positive terminal and N side of the semiconductor to the negative terminal, while the collector junction is reverse bias by connecting P side to the negative terminal and N side connected to the positive terminal. VEB, voltage developed across emitter base junction. VBC, the voltage across base and collector junction. So emitter junction is forward bias, the collector junction is reverse bias. Come back to working of this transistor. As the majority charge carriers in P side of the semiconductor are holes, these positively charged holes are repelled by the positive polarity. They move towards the junction. All the holes try to move towards the junction. These holes enter into base, where maximum number of holes combines with less number of electrons that are present in the base, where they gets neutralized, producing a small base current IB. Still some more holes are left over. These holes enters into collector. Again, collector is of P type, in which the majority charge carriers are holes. All these holes in the collector P type are attracted by the negative polarity. They move towards the negative terminal, giving a large collector current IC. So IB is base current and IC is a collector current. Electrons and moreover, as this emitter is a heavily doped region, number of covalent bonds are more. For example, when one single covalent bond breaks, one electron and one hole will be liberated. As this emitter P type is heavily doped region, for suppose 100 covalent bonds breaks, as it is connected to the battery, 100 holes and 100 electrons are liberated. Those 100 holes, those 100 electrons which are now generated in the emitter P side are attracted by this negative polarity. They move towards the positive polarity, giving a large emitter current IE. The holes then again enter into collector. These holes are again attracted by this negative polarity, giving a collector current IC. The process continues so on, such that the relation between different currents produced in this transistor is emitter current is equal to base current plus collector current. This is the working of PNP transistor. In case of this NPN transistor, emitter is N type, base is P type, the collector is again N type. Majority charge carriers in emitter P side are electrons. while the minority charge carriers are holes. As the base is made up of p-type, majority charge carriers are holes and minority charge carriers are electrons. The collector again is made up of n-type, in which electrons are the majority charge carriers holes are minority charge carriers. In case of this NPN transistor, emitter junction is forward bias by connecting P side to the positive terminal, N side to the negative terminal, while the collector junction is reverse bias by connecting P side to the negative terminal and N side to positive terminal. So the emitter junction is forward bias, the collector junction is reverse bias. Come back to working of this transistor. As emitter n-type is connected to the negative terminal, the majority charge carriers in this emitter n-type are electrons. These electrons in emitter n-type are repelled by the negative polarity. They try to move towards the base. The base is made up of p-type, in which the majority charge carriers are holes. These electrons from the emitter n-type, they recombine with less number of holes present in the base p-type, where they recombine with holes, giving a small emitter current IE. The remaining electrons then enter into collector. Now, a large number of electrons are now present here in this collector n-type. All these electrons are attracted by the positive polarity. These electrons move towards the positive terminal, giving a large collector current IC. Since this emitter n-type is a heavily doped region, as if one covalent bond breaks, as I told you just now, one electron and one hole will be liberated. For suppose if 100 covalent bonds breaks, 100 electrons and 100 holes are liberated. Those 100 electrons in this emitter n-type are attracted by the negative polarity. They move towards this negative terminal, giving a large emitter current IC. The electrons then enter into collector. All these electrons are attracted by the positive polarity, moves towards the positive terminal, giving a large collector current IC. The process continues so on, such that the relation between various electric currents in this transistor is emitter current is equal to base current plus collector current. So this is the working of NPN transistor. The applied input AC power of a half-wave rectifier is 100 watts. The DC output power is 40 watts. You are asked to calculate efficiency. The given options are A 20%, B 40%, C 30% and D 60%. The formula for efficiency: eta is equal to DC output power by AC input power, that is eta is equal to DC output power is given as 40 by AC input power is 100, that is 0.4. Therefore, efficiency eta is equal to 40%. The option second one is correct. A full wave rectifier uses two diodes with load resistances 100 ohms. Each diode is having a negligible forward resistance. Find its efficiency. The given options are 71.2%, 81.2%, 91.2% and none. Now, according to the data given, load resistance as 100 ohms. Each diode is having a negligible forward resistance. It is RF, you can take it as 0. You are asked to calculate efficiency. In case of full wave rectifier, the formula to calculate efficiency is 0.812 into RL by RF plus RL, that is 0.812 into load resistance is given as 100 by 100 plus 0, but you will get it as 0.812. So the efficiency of the rectifier is 81.2%. So second option is correct one. A band gap corresponds to minimum energy required to push an electron from valence band to conduction band. You are asked to calculate. The given options are 7.02 10 power minus 20 joules, 8.02 10 power minus 20 joules, 7.02 10 power minus 15 joules and 8.02 into 10 power minus 15 joules. According to the formula for energy, E is equal to Hc by lambda. The value of Planck's constant is 6.63 10 power minus 34 joule second. The velocity of light 3 into 10 power 8 meter per second by 80 10 power minus 9. When you simplify this, you will get the answer as 8.02 10 power minus 20 joules. So the option second one is correct. Next one, at 25 degrees centigrade, the potential barrier for silicon is given as 0.6 volts. You are asked to calculate the potential barrier when the temperature is maintained as 125 degrees centigrade. The given option is 0.5 volts, 0.3 volts, 0.7 and the last one 0.8 volts. The relation between volume and temperature, potential and temperature is potential directly proportional to absolute temperature. From this I can write V1 by V2 is equal to T1 by T2. According to the given data, potential first case 0.6 volts, V2 you are asked to calculate. Temperature, initial temperature is 25 degrees centigrade. So 273 plus 25 plus 25, it becomes 298 kelvins. The value of T2 is given as 125. So 125 plus 273, it becomes 398 kelvins. Now substitute this data in that relation. From this relation, V2 is nothing but T2 by T1 into V1. Therefore, V2 is equal to T2 398 by 298 into V1 is 0.6 volts. When you simplify that, you will get a final potential as 0.8 volts. So, fourth option is the correct one. In an unbiased PN junction diode, the thickness of the depletion layer is 7×10⁻⁶ meters and the potential barrier is given as 0.7 volts. You are asked to calculate the magnitude of electric field. The given options are 10⁶ volt per meter, 10⁵ volt per meter, 10⁴ volt per meter and 10⁻³ volt per meter. Now, according to the given data, barrier potential V is given as 0.7 volts. The thickness of the depletion layer, thickness D is given as 7×10⁻⁻⁶ meters. Electric field you are asked to calculate. According to the relation between electric field, potential difference and thickness or the distance, and write E is equal to V by D. V is given as 0.7, the thickness as 7×10⁻⁻⁶. So we get E is equal to 10⁵ volt per meter. So the option second one is correct. Next one is, in a half-wave rectifier, the load resistance is 90 ohms. If the diode forward resistance is 10 ohms, find efficiency. The given options are A 32.54%, B 36.54%, C 38.54% and D 30.54%. Now, given load resistance RL as 90 ohms, the diode forward resistance is 10 ohms. Resistance of the diode in forward resistance is given as 10 ohms. You are asked to calculate efficiency. For a half-wave rectifier, the formula for efficiency is 0.406 into RL by RF plus RL. Substitute the values. 0.406 into load resistance is given as 90 by diode forward resistance is 10 plus 90. When you simplify this, you will get around efficiency as 36.54%. So second option is the correct one. In a full wave rectifier, the load resistance is 800 ohms and the diode forward resistance is 200 ohms. Find efficiency. These are the four options: 54.96%, 44.96%, 74.96% and 64.96%. Efficiency in case of full wave rectifier, the formula is 0.812 into RL by diode forward resistance plus load resistance. According to the data given, load resistance as 80 ohms, the diode forward resistance is given as 200 ohms. Efficiency you are asked to calculate. Substitute the values in this relation. Efficiency eta is equal to 0.812 into load resistance is 80 by diode forward resistance as 200 plus 80. When you simplify that, you will get efficiency nearly about 64.96%. So the fourth option is the correct answer. Sir, a transistor has alpha value 0.995. You are asked to find beta. The given options are 0.95, 199, 19 and 1.9. In case of transistor, the relation between alpha and beta is equal to alpha by 1 minus alpha. That is, alpha is given as 0.995 by 1 minus 0.995. When you simplify that, approximately the value of beta is going to be 199. So the second option is the correct one. So in a half-wave rectifier, a load resistance is 1 kilo ohm and internal resistance of the rectifier is given as 10 ohms. You are asked to calculate efficiency. The four given options are 30.2%, 40.2%, 50.2% and 20.2%. Half-wave rectifier efficiency. The formula for efficiency of half-wave rectifier is 0.406 into load resistance by diode forward resistance plus load resistance. According to the data given, the load resistance is given as 1 kilo ohm, which is equivalent to 1000 ohms, and the internal resistance, that is RF, is given as 10 ohms. The efficiency of the rectifier you are asked to calculate. Substituting the data in this relation, we get eta is equal to 0.406 into 1000 by 10 plus 1000. When you simplify this, nearly you will get the efficiency as 40.2%. So the second option is the correct one. In an NPN transistor, the values of base current is 100 microamperes and collector current is 9 amperes given. You are asked to calculate emitter current. The given options are 8.1 milliamperes, 10.1 milliamperes, 4 milliamperes and 9.1 milliamperes. First, emitter current. The relation between different currents in NPN transistor is emitter current is equal to base current plus collector current. Given base current as 100 microamperes, which is equivalent to 0.1 milliamperes, because the collector current is expressed in terms of milliamperes, so I converted base current in terms of milliamperes, and the collector current is given as 9 milliamperes. The value of emitter current you are asked to calculate. Since emitter current is equal to base current plus collector current, I am substituting 0.1 plus 9. So the magnitude of emitter current is 9.1 milliamperes. Fourth option is the correct one. For a transistor, the value of beta is given as 99. You are asked to calculate the value of alpha. The given options are 0.99, 1.99, 2.99 and none. In case of a transistor, the relation between alpha and beta is alpha is equal to beta by 1 plus beta. The value of beta is given as 99 by 1 plus 99. That is 99 by 100. That is 0.99. So the first option is correct one. Next one. In a common base transistor, the current gain is 0.98. In charging the emitter current, in changing the emitter current by 5 milliamperes, you are asked to find the change in the collector current. The options are 2.9 milliamperes, 4.9 milliamperes, 6.9 milliamperes and 3.9 milliamperes. In case of a common base configuration of a transistor, the change in the collector current is alpha into the change in emitter current. Given the current gain alpha is 0.98, the change in the emitter current is given as 5 milliamperes. You are asked to calculate change in the collector current. So change in the collector current is alpha 0.98 into 5. So the change in the collector current in this case is 4.9 milliamperes. So second option is correct. Next is a Zener diode. Zener diode is a heavily doped silicon p-n junction diode which is operated only in reverse bias condition. A heavily doped silicon p-n junction diode that is operated in reverse bias condition is called Zener diode. Symbolically, this is the representation of a Zener diode. Now we shall discuss about the VI characteristics. VI characteristics of Zener diode. VI characteristics, the voltage current characteristics of a Zener diode. Forward voltage, reverse voltage, this is a forward current and reverse current, currents in reverse bias. This is origin, the forward characteristics, the reverse characteristics. This Zener diode is heavily doped in a reverse bias condition. If you look at this graph, the forward bias characteristics. Forward bias characteristics of this Zener diode is almost identical to the forward bias characteristics of p-n junction diode. As you can clearly see from the diagram, in case of forward bias condition, with increase in the forward voltage, the forward current also gradually increases. With increase in the voltage, the current also increases in the forward bias condition. Whereas in case of this reverse bias condition, with the voltage, with increase in the voltage, the reverse current remains zero almost for a certain period of time. With further increase in the voltage in the reverse bias condition, the reverse current suddenly rises exponentially. This voltage applied across the Zener diode when operated in reverse bias condition, at which the reverse current suddenly rises to exponential, is called Zener breakdown. Zener breakdown. The voltage applied across the Zener diode in the reverse bias condition at which the reverse current suddenly becomes exponential is called Zener breakdown voltage. This Zener diode is effective only when it is operated in reverse bias condition. Now we shall see how this Zener diode can be used as voltage regulator. The Zener diode can be operated as voltage regulator only when it is operated in reverse bias condition. See here, let us consider a Zener diode. Let the load resistance RL be connected across the diode. Here capital R represents the series resistance. The input voltage is applied across here, the primary, while the output voltage E0 is collected across the load resistance. Let I be the total current. This total current is getting divided into two parts as the current through the diode and the current through the load resistance. So the total current I can be written as the current through the diode plus the current through the load resistance. Here the output voltage can be written as the difference of input voltage minus I into R. Moreover, in this case, when this Zener voltage is operated in the reverse bias condition, output voltage is equal to the voltage applied across the Zener diode. And further, the series resistance, the value of series resistance R can be calculated as EI minus E0 by IZ plus IL. This is input voltage, output voltage, the current through the Zener diode and current through the load resistance. Here EI minus, as voltage across the output is always equivalent to the voltage across the diode. In place of E0 I am writing VZ. And as the total current is getting divided into two parts as the current through the diode and the current through the load resistance, in place of IZ plus IL I am writing total current I. So these are the values of total current, input voltage, the series resistance applied across the diode and the output voltage. This is how the Zener diode can be operated as voltage regulated only when it is operated in reverse bias condition. 4 silicon diodes are connected as shown in the figure. Assuming the diodes to be identical, find the current through the resistance capital R, series resistance capital R. As you can see here, the voltage applied across all the diodes is 5 volts. You are asked to calculate the current through the series resistance capital R. According to the given data, assuming diodes to be identical, since all 4 diodes are identical, the current through all of them is negligible. I can suppose that as all the diodes are identical, the current through all these 4 diodes, is negligible. Further, given voltage V is equal to 5 volts. Series resistance R is given as 50 ohms. You are asked to calculate the current through the resistance capital R. According to Ohm's law, I is equal to V by R. V is given as 5, the resistance is 50. So, the current through the series resistance R is 0.1 amperes. So, the first option is correct one. The comparative study for common base, common emitter and common collector amplifiers is shown in this tabular column. First, the parameter. The first parameter is input resistance. In case of common base amplifier, this input resistance is minimum, which lies from 50 to 200 ohms. Input resistance for common base amplifier. For common emitter amplifier, this is very less when it lies between 1 to 2 ohms, 1 to 2 kilo ohms. While in case of a common collector amplifier, this input resistance lies in between 150 to 800 ohms, 150 to 800 kilo ohms. Okay, this is the parameter input resistance in case of all these three amplifiers. The next parameter is output resistance. Output resistance in case of common base amplifier is 1 to 2 mega ohms. For a common emitter amplifier, 5 to 50 kilo ohms, and for a common collector amplifier, it is minimum about 1 kilo ohm. The next parameter is current gain. The current gain for common base amplifier is minimum. For common emitter amplifier, the current gain is from 2 to 200, and which is maximum in case of common collector amplifier. The next parameter is voltage gain. The voltage gain in case of common base amplifier is medium. In case of common emitter amplifier, the voltage gain is high. For a common collector amplifier, the voltage gain is minimum. The next parameter is power gain. Power gain for common base amplifier is medium, which lies in between 20 to 30. In case of common emitter amplifier, which is a maximum, which lies in between 30 to 40, and finally in case of common collector amplifier, its value will be nearly 10. And the last parameter is phase interval. The phase interval for a common base configuration is 0. There is no phase interval or phase difference. For a common emitter amplifier, the phase interval lies, while there is no phase interval in case of common collector amplifier. So, these are the comparative study of all the three configurations of transistors: common base, common emitter and common base, common emitter and common collector amplifiers. Next problem. According to the given data, these two are the diodes D1 and D2. This circuit consists of the two diodes, each with a diode forward resistance of 50 ohms. The diode forward resistance for these two diodes is given as 50 ohms, and with infinite resistance in reverse bias. If the voltage of the battery connected across these diodes is 6 volts, you are asked to calculate the current through the diode, current through the resistance of 100 ohms. The given options are 0.01 amperes, 0.02 amperes, 0.03 amperes and 0.04 amperes. According to the data given, these two diodes have same resistance operated in the forward bias, but with infinite in reverse resistance. The applied voltage across the battery is 6 volts. Now, the equivalent circuit for this diagram I have drawn here. Since the diode D1 is forward bias, the current through D1 is maximum. As the diode D2 is reverse bias, the current through D2 will be minimum. And moreover, as all the resistances 150, 50 and 100 ohms, all these resistances are connected in series, the current through all these resistances will be same. So, you are asked to calculate the resistance through 100 ohms. As the same current flows through all the resistances, since they are connected in series, I can write according to Ohm's law, I is equal to V by R. Here, as we are having 3 resistances, moreover they are connected in series, I can write I is equal to V by R1 plus R2 plus R3. That is, voltage is given as 6 volts by R1 is 150 plus R2 is 50 plus R3 is 100. So, when you simplify, you will get nearly 0.02 amperes. So, the conclusion is the current through the resistance 100 ohms is 0.02 amperes. So, the second option is correct one. In a silicon diode, the reverse current increases from 10 microamperes to 20 microamperes. When the reverse voltage changes from 2 volts to 4 volts, find the reverse AC resistance across the diode. The given options are 1 into 10 power 5 ohms, second option 2 10 power 5 ohms, third one 3 10 power 5 ohms and last option 4 10 power 5 ohms. According to the data given, the change reverse voltage changes from 2 to 4 volts. So, the change in the voltage V is equal to 4 minus 2, that is 2 ohms. He further said that the reverse current changes from 10 to 20 microamperes. Change in the current delta I is equal to 20 minus 10, that is 10 microamperes. 10 microamperes, which is equivalent to 10 into 10 power minus 6 amperes, that is 10 power 5 amperes. You are asked to calculate the reverse AC resistance of the diode. Therefore, the reverse AC resistance of diode is R is equal to resistance is equal to V by I. So, change in the voltage by change in the current. What is the change in the voltage? We got 2 by the change in the current is 10 power minus 5. So, the reverse AC resistance of the diode is 2 into 10 power 5 ohms. Therefore, the second option is the correct one. Next problem, in a p-type semiconductor, the acceptor level is situated 60 million electron volts above the valence band. You are asked to calculate the maximum wavelength of light required to produce a hole. The options given are 0.207 10 power minus 5 meters, 2.07 10 power minus 5 meters, 20.07 10 power minus 5 meters and none. The maximum wavelength you are asked to calculate. Now, the maximum wavelength of light required to produce a hole. The maximum wavelength of light required to produce a hole can be obtained by using the relation E is equal to hc by lambda. As we are asked to calculate wavelength, lambda is equal to hc by E. Here h is Planck's constant whose value is 6.6 10 power minus 34 joule second. The value of speed of light is 3.8 10 power 10 meter per second, then 3.8 10 power 8 meter per second, and the energy is given as 60 million electron volts. So 60 million electron volts is equivalent to 60 into 10 power minus 3 into 1.6 10 power minus 19, converting million electron volts into joules. Now, when you simplify this, you will get the answer as 2.07 10 power minus 5 meters. So, the wavelength required to produce a hole is 2.07 10 power minus 5 meters. So, the second option is correct one.